First, again, a reminder that on Monday, the lecture takes place downstairs in a basement in the room B23. So this room will be busy with some conference or something. And all the pictures you sent, you can find on Blackboard. I just picked 4, which caught my eye. This one is really neat. I always envy people who can draw nice pictures. This is simple and informative. This looks just like a copy of my picture. So if it is a copy of my picture, it doesn't really help to manage the material. This is a very interesting approach. I always say, if you're not sure how to do algebra, pick a numbers, and the student picked numbers and used numbers to visualize what is happening. Very smart. And a question to you is about work done by electric field on an electron when the electron has been moved. How? We don't care. Maybe it was magic. Maybe someone physically moved it. All we know is that the initial electric potential was this, and final was that, and we know the equation. And the work is a number, as any number, real number. It only can be negative, positive, or zero. Sometimes we may need some extra information. Last call. If nobody takes it back, I'm going to put it in the lab room. That's it. And again, I need to remind you that if you know what to do, you just do it. If you're not sure, if you need more information, you should, what? You have a question? You look like you have a question. You know? Ask a question. Ask a question, any question, just ask a question. Ask a question.
Yeah, what we were saying.
What I was saying that every time when you're not sure, you should ask a question. That's what I said. Well, we have all possible answers except 2. Someone should choose 2. 2 feels lonely. 2 would be wrong, of course. Well, but positive or negative? The equation tells us all we have to do is just plug the numbers, a charge. So we moved it. That's the initial location, that's the final location. How did we move it? Was it a straight trajectory? Or oops, no jumping? It was flying in space until it gets to the same final location. First of all, does it matter? No. The equation only relates to a charge, initial and final values of the potential. And here the initial potential was 1,000 volts and the final potential 5 100 volts. So we need to write those numbers in the parentheses. This is not a 9, this is a Q, a charge. And the result, of course, depends now on the value of this charge. So anybody, please tell me, what is the value of this number, Q? Or at least what is the sign of it? How do we know? How do we know? How do we know? Exactly. And Google. If we're not sure about properties of a particle, we have many different particles: an electron, a proton, a neutron, alpha particle, beta, gamma. We will talk more. But if you read a name, all you have to do is just search. All properties for all particles have been, of course, established. And for the electron, the magnitude of this charge, this is what we call the elementary charge. The charge of a proton, actually. A charge of an electron is negative E. That's how people write it down. So we need to multiply two numbers, a negative and a positive. And that should give us a negative result. Again, a negative charge. I'm going to give you time to read and start thinking about it. A negative charge, a given magnitude, accelerates in an electric field. Certain work is done. The initial potential is given. We need to find many different things. Well, first of all, it doesn't really matter what we are looking for. Eventually, we'll find anything we want to, except happiness. But well, it's just a fact. The question is, what is connected to what? So the connections are important. And it is kind of good habit to be able simultaneously read a text and transfer every important piece of information into some symbol, some notation, like a negative charge, okay. Accelerates in a constant electric field. Constant. We don't know if it's important, maybe not. Sometimes it's not important, sometimes it might be important. And we don't think about that right now. The process we do right now is translation. The work, joules, the initial potential, 100 Voroshilovs. Other variables which are involved: final potential energy, distance traveled, the strength of the electric field, the mass of this charge, speed. There is also one number which is assumed. If we say something about the initial speed, probably we should immediately say something about what? I mean, final speed. I gave away the answer. If we say something about final speed, we should say something about the initial speed, and that should be 0 released, I think. accelerates, well, assumed from rest. All right. All of these variables are connected, of course, and in physics, a connection is presented by an equation. An equation might be a definition of something or a law. Here, well, one equation is already given. Bless you. It's a combination, actually, of two definitions. It's a combination of a definition of what electric potential is and a definition of what electric potential energy is, or initial, final. And, well, we write an equation. The natural thing is try it out. If it gives certain number, gives a new information, good. If it doesn't, we start thinking further. So every time well, writing is an action. We finished some action, and we ask the same question, what can we do now? Well, now we can plug numbers in. That's another action. 5 times 10 to the negative third equals a charge, which is negative, times initial voltage, potential. Voltage is in several slides. Minus final potential. It turns out, actually, it's a very simple algebraical equation. We can solve it for the final potential. It should be equal to (100 plus 5 times 10 to the negative third over 5 times 10 to the negative sixth. I do it in my head because I don't have much space for writing, but you should write in your notebook all steps necessary to check, because I might make a mistake. And as you know, everybody makes mistakes. Mistakes are inevitable and unavoidable. There is no shame in making a mistake. There is a shame in sticking to that. That's it. So, 5 over 5, 1,000 and 1,100 volts. So the first unknown is here. Now, potential energy. A straightforward definition tells us how to calculate potential energy. The initial or final doesn't matter. Let's do both. That's, oh, the charge is the same. That's the initial potential energy, negative 5 times negative 6 times initial potential was 100. So negative 5 times 10 to the negative 4 joules. Final potential energy. Final negative 5 times 10 to the negative 6 times 1100. So negative, still negative, 55 times 10 to the negative 4 joules, right? If I break it 11 and 100, yes. Which energy is higher? Which energy is lower? Well, this is how we think about negative numbers. Yeah? On a negative scale, so this is negative 5, that will be negative 55, right? So we know that when a charge is released, well, any object in potential field is released, on its own, it starts traveling from location from high potential energy to location with low potential energy, like a ball falling down. What else? Okay, I think I have an extra slide. Yes. So what's next is, I have to check it. Yes? Yes. Electric field strength. Well, here's the fact that it is uniform important, because for electric field strength, as we know, and we will talk about it again, the equation is simple. So 1,100 minus 100 divided by 0.1, 10,000, right? 10 to the fourth. Now, we used to write a unit, a Newton over a Coulomb, because it's force over charge. However, now, if we look at this equation, it also is a volt, a unit of the volt of the potential over a meter. And if you try to use unit analysis, you can prove that's exactly the same unit actually. And if you see a Newton over a Coulomb or a volt over a meter, don't be confused, same thing. Where else? Speed. We have so many venues to answer that question. We can use Newton's second law because we know the mass, we can calculate acceleration, we know distance, we can relate distance, acceleration, initial speed, final speed. Also, we can use energy conservation. That usually is the fastest approach, because we know work, and because we know no other forces acting on it. Well, that's assumed. We can apply the work kinetic energy theorem. The work kinetic energy theorem tells us that the change in the kinetic energy should be equal to the net work. In this situation, the only work is this work, which is 5 times 10 to the negative third, and the kinetic energy final minus kinetic energy initial should be equal to that number. Now, again, we should keep track of the meaning of each letter V we write. Potential, volts, speed. So speed will be equal to square root of 2Wm, which is, I don't know, 2, 5, negative third, 10 grams, 0.01. 2 times 5 is 10. So 1, negative 3, and 10, negative 2, negative 2, negative 2. I think it's 1. You have a calculator, you can check it. Don't trust me. Never trust anybody without calculator. Hmm?
It's 1.
Any questions? Technically, we have solved several different problems in one, but there's one more similar example, all right? So again, please read and try to make a translation of this text into symbols you will use later. Yes?
The previous slide, I just didn't understand where you got 2.5.
Hmm?
Where you get 2.5 from? Oh, 2 times 5. Sorry.
Yeah, that's a yeah, 2 times 5 times. Yes?
What's the equation you got for the last?
This is the equation. This stands for work kinetic energy theorem. You should open the, I don't know, notes and type it in and then search for that, because this comes from PY 105. This is a relationship between kinetic energy initial, kinetic energy final, and the total work done. So you should literally search. That's it. It's in any textbook. Any. So we take this from the past and we use it now. Work, kinetic energy, theorem. Change in the kinetic energy is equal to the net work done on the object of the system. Please, again, it's a, again, good habit. Try to do it at the same time. Yeah. Read and write. Read and write. Make it translation of a textual information into a symbolic one. Charge. At rest, electric field strength. Okay, it moves to the right. Velocity points to the right. Velocity. Mass. Distance. 10 centimeters. Oops, come back. And again, there are several different approaches we can use to solve this problem, because on one hand, we need to relate distance, initial velocity, final velocity, distance, initial velocity, final velocity, also a part of acceleration, time, displacement, batch of variables from PY 105, which implies we could have used the Newton's second law, because acceleration is a part of it, and a force is related to, as we know, electric field strength and a charge. That's a dynamical approach. We also could use the same approach we've used before, just several minutes ago, using energy, because, as we know, speed, initial and final, related to kinetic energy. Kinetic energy is related to work, well, net work is related to any individual work, and work is related to also a charge, same charge as here, but also related to initial potential, final potential, and initial potential and final potential also related to distance between the points and electric field, which is the same. So we've got so many equations available for us. So basically we just have to pick one and try it out. If it doesn't give an answer immediately. We have to pick another one and try it out and again and again. And after practicing for many, many years, in a problem like that, you know what equation should you pick first. That's it. And I want to pick the equation which has a name, work kinetic energy theorem, just to practice using that equation. Bless you. Work kinetic energy theorem tells us that final kinetic energy minus initial kinetic energy should be equal to the net work. But if only one force acting on it, net work is just the work of that single force. In this situation, that's electric force. And as we know, electric force does work which is equal to a charge times initial potential minus final, potential. Any questions on this part? Why did I write this equation? What is the reason? There is one reason, because I want to. And I hope it's going to help. More than hope. I believe it's going to help. More than believe. I know it's going to help. Why? I've done it before. That's the only reason. So if you've done something similar before, you will be confident. Right now, what else do we need to do? Well, first of all, let's see how it works for us. Mass, final speed squared over 2, charge. And here, what we usually write is, it's not a change, it's a difference, a potential difference. Change would have been final minus initial. So I don't want to write final minus initial because that would be negative here. So that's the change. And as we know, this from the past here, that equation on the left, the potential difference, distance between 2 points, and electric field strength are related. Now, to use that equation, I need to make sure those points lie on the same field line. In my situation, that requires a picture. So this is my charge. Positive, right? Positive. If it starts moving to the right, that means the force acting on the charge propels it to the right. If it's a positive charge and force points to the right, that means acceleration points to the right, yes. Velocity points to the right, yes. But also that means electric field points to the right. So electric field line should look like this. Well, it has no end. Yeah. So that's the initial location. So we're here. It will traveling at that speed. And if no force is acting on it, it just should keep traveling straight ahead. So the initial and final location do lie on the same electric field line. So we can write this equation. We just have to solve it for, again, potential difference, which is supposed to be equal to the product, strength times distance. So Q, strength, distance. And now we are all set. This is where I sometimes like to write physics is done, which means my job here is done, which means I'm just moving on. Here, so we saw this yesterday. If electric field is uniform or almost uniform, That's how we can calculate electric potential energy under certain conditions, which are not really important. According to a definition of electric potential energy over charge divided by the value of that charge gives electric potential. This is an expression for electric potential of electric field when the field is uniform, when the axis points parallel to field. So this is a mathematical proof. Now we can make a leap of faith here. If electric field is not uniform, for example, electric field of a point charge, it changes, it decreases with distance. But we can reason through using some calculus or calculating areas, and we can derive this equation. From that equation, if we break the whole field into small portions and then treat each portion like uniform and then do like integration, we can get this equation. This electric potential of a point charge. Same constant, a charge which generates electric field, not the magnitude, the actual value. And this is a distance from a charge to a location where we're calculating or measuring electric potential. For a negative charge, the equation is exactly the same, but because the charge is negative, electric potential will give negative values, that's it. And R represents a distance. Distance is never negative. So if we move away from a charge at a certain distance and walk around in circles, keep the distance the same, the electric potential should be the same. So we have an infinite number of locations with exactly same electric potential. Well, in this picture, it's a surface, a sphere, spherical surface. A surface like that has a name, the equipotential surface. Equi means same, potential means potential, equipotential means same potential. Well, actually, here you can see these spheres represent equipotential surfaces, or shortly, equipotentials. And these lines represent electric field lines of a positive charge. And you can see that the electric field lines, well, first, they point, we know they point away from a positive charge, but also we know electric potential close to the charge should be higher, lower, so electric field lines point from high potential to low potential. Yes?
The reason that the
That I do not understand. For electric field, that's a good question, but I don't understand the question, but it's a good question. For electric field strength, we know the equation. So if I want to calculate electric field strength at different distances, I'm going to get different numbers. Different strength means it changes. It changes means it is not uniform. The word uniform means it does not change. It's the same everywhere. Everywhere means literally everywhere. If you have two locations and electric field strength is different, that's it. That cannot be uniform by definition of the word uniform. The graph for electric field strength of a point charge looks like this, a hyperbola. It changes. For a negative charge, we also have spheres as equipotentials, but negative potential. And again, we can see that now, again, electric field points from high to low and perpendicular to equipotentials. And we can extend this knowledge to many charges. What if we have several charges? Well, it's very simple. We just need to calculate electric potential generated at the same point from each charge and add them up together. We just need to remember, if we need to do that, Q's, Q1, Q2, Q3, represent an actual value. So it could have been positive or negative, not a magnitude. And electric potential is a number, not a vector. It doesn't have a direction. It's just a number. 5 volts, negative 10 volts, 120 volts. So let's just practice. Again, a dipole. We've seen electric field of a dipole. Let's calculate electric potential at 2 different locations. I'm going to start from location B. Let's call it a positive charge and a negative charge. And electric potential at point B should be equal to electric potential at point B from a positive charge plus electric potential at point B from a negative charge. That's also called overlapping or superposition. Superposition. And, well, Q plus over RB plus K, Q minus over RB minus. What is K? The K is a constant. What is Q? Q represents a charge. In the first term, that's supposed to be a positive charge. And that's supposed to be a distance from that charge to the location where we are calculating electric potential of that charge. And from plus to B, it's 0.4. 0.4 period, not squared. See, the equations for electric potential and electric field strength very similar. Very similar, but not exactly the same. Now we need to add. This plus means this plus, this plus means this plus. What do we need to add? We need to add the electric potential of a second charge generated at the same point B. So the distance now has to be measured from a negative charge to point B. Now we have to take a calculator and add these two numbers. And the result is 0. They cancel each other out. That's not the only location with 0 potential. For example, if I choose a point C here, I'm going to get 0 again. Because, again, the distance R1 and R2 will be equal to each other. And potentials, again, cancel each other. So this line represents an equipotential with potential equal to 0 volts. Any point on this line has exactly the same potential, and that potential equals to 0. Okay, point B done. Point A, exactly the same type of reasoning. Electric potential at point A should be equal to electric potential at point A due to the positive charge plus electric potential at point A due to a negative charge. So we will Just plug the numbers in. Same charge, but distance now is different. And from plus to A, the distance is 0.2 plus 9 times 10 to the 9th. A charge is negative, and the distance from minus to A equals what number? 0.6. So now we just have to finish this calculation, and the answer is 240. See how fast I can calculate in my mind. And of course, that's not the only location with same potential. We can find more locations where potential is equal to 240 volts. They lie on like a hyperbola, not a straight line anymore. And if we map different lines with the same potential, this is what we would see. Red lines we've seen before, same old electric field lines. And blue lines here represent locations with the same potential. Potential here is different from potential here, of course. When we move away, potential changes. Actually, from high to low, in the direction of electric field, potential decreases. But from here to here to here to here to here to here, electric potential will be the same for a dipole. Any questions? Yes?
Can we go over what's the difference between electric potential and electric potential? The one that has the R squared.
No,
Okay.
because it has nothing to do to conceptual understanding. It's about definition. So it's not conceptual, it's memorable. A definition of electric potential is electric potential is equal to electric potential energy of a positive 1 coulomb charge. That's a definition. That's what it is. And then from this, we write a relationship. Electric potential energy of any charge will be equal to electric potential energy of 1 coulomb charge times the charge. But electric potential of 1 coulomb charge, we now called potential, just to call it shorter. And that's how we get an equation, U equals QV. Yes?
Can we go back a few slides? Too fast about the
If you, that's too many. You mean this slide?
Yes.
In this slide, I'm not going to spend too much time on it because this we discussed yesterday, so you have to review that. And here I only said there is a mathematical method which leads to this. And that mathematical method is outside of the scope of our course. That's it. That's all we need to know. That has been proved. That can be proved. Okay, this is an example how we can analyze the picture. As I said, when electric potential changes, the easiest way to see how it changes is to bring the points with the same potential on the same field line. For example, here, I know that here and 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 here, the electric potential is supposed to be equal to this number. And I know that here and 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 here, the electric potential will be equal to this number. And I know that electric field lines point from a higher potential to lower potential. And now, if I move a charge, in this situation a proton, what do we know about proton? It's a positive charge. Technically, again, everything. Mass 1.67 times 10 to the negative 27 kilograms. So for electron, you Google 9.1 times 10 to the negative third kilograms. So a proton is a positive charge. So if we need to calculate work, Q, V initial minus V final. But if we move a charge from here to here, and it doesn't matter how, the initial will be V2, and the final will be V1. So we're multiplying two positive numbers, should be positive. Switching which sign? No, I didn't. No, I didn't. You see, you who told you that 1 always means initial? Did I tell you that? That's a yes or no question. Did I tell you that number 1, subscript 1, always means initial? See? From, this English word means initial. To, that means final. If we move an object from here to here, that makes this point to be initial and that point to be final. And how did we call those points? 100 and 1,000, or 500 and 1,000, or V1 and V2, or something else. For example, I could call it V big and V bigger. In fact, it's smaller. But I didn't know that. It's a matter of what I want to do. Calling. But still, if I start my motion here and I finish my motion there, this potential will be initial and this potential will be final. Think about it. Now, I promised you to go back to the equation which relates potential difference, distance, and field. A promise is a promise. So this equation has been proved, and this equation is just a use of that equation. So let's say this charge moves from x initial to a new location with x final. We can set 0 anywhere we like. Normally we set x equals 0 where potential is 0, or we set potential 0 at x equals 0. And in this situation, if we want to calculate this difference, V initial minus V final, that should be equal to V initial equals this times x initial minus, and V final equals this times x final. How do I know? I used this equation. This equation came from that equation. That equation came from something else. There's always a chain of reasoning, and technically the parts of that reasoning should be stored in different cells of our memory. So mathematics tells us it should be equal to minus, and minus makes it plus. So E times x final minus E times x initial, or E times delta x. Technically, this difference is negative delta V. we have to stick to definitions. Initial minus final doesn't really have a name. People call it difference, but not everybody. But everybody calls change final minus initial. And everybody uses this symbol, delta, little triangle, Greek letter, for the word change. So technically, this is what we should write down. But of course, who cares about signs? Much easier, just use magnitudes. In that case, we will never make any mistakes with the plus or a minus. Or, as we had it before, D is the distance. Distance is never negative. Just a little bit of algebra. So this is a very important result. That's why I have another slide which says exactly the same thing. And now I have a question. These, what color is that? All right. These pink lines represent equipotentials, or we can say equipotential lines. So electric potential here, 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 here is 20 volts. Electric potential here, 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 here is 10 volts, etc., etc. We also know the distance between those lines, and it's the same everywhere, which means this electric field is uniform. The question I want to ask you is, what is the direction of that electric field? Electric field lines, electric field vector. You can choose from the set of these directions. I want to choose this. You should tell me if this choice is right or wrong.
Let me think more.
Okay, of course. What do you think?
I was thinking the same one because the absolute value of.
So you agree with my arrow? Okay, thank you. It makes me feel better. What do you think? What do you think? You should choose carefully who you agree with.
It should points down.
Yeah, same.
So first of all, every question in physics is based on a rule. Sometimes it's a verbal rule, sometimes it's an equation. These are the rules. Do you have a copy of the rules in your notebook? No, you need a copy of the rules in your notebook. How do we make a copy?
My own words.
You can't use your own words. No one in physics can use own words. That's prohibited. You only can use the words which have been used for hundreds of years because they worked. If you replace any word with your, that's it. It will be your law. If it works for you, fine. But I doubt it will work for you. You have to follow literally every word of every rule. In that case, you will be all set. That's what's good about physics. You don't really have to think about anything. Physics doesn't involve thinking. So, rules. Equipotential lines and electric field lines must be perpendicular to each other. An electric field point from a higher potential to a lower potential. So, do you still agree with this arrow? If you disagree, you have to say out loud the reason. What part of a rule is broken? All right, it's not perpendicular. It is not perpendicular. What about this arrow? Now it is perpendicular. Is it the correct arrow now?
No.
Why? It breaks a second part of a rule. So we have to, technically it's again, same old, trial and error method. We have to try all arrows and eventually we get one which will work, which will not violate any part of any rule. So that's going to be 7, right? From high to low, perpendicularly. So electric field should point like this. And to calculate the magnitude, of course, we just need to write an equation. Electric field strength equals potential difference. Let's say this is my point number 1. This is my point number 2. And magnitude, it's going to be 10 minus negative 10 divided by distance. This distance is equal to 20 centimeters, another 20 centimeters, 20 centimeters, 20 centimeters. So a Pythagorean theorem, square root of 2 times 20, 0.2, I need to use meters. So 20 over square root of 2 of 20, 1 divided by square root of 2, 0.7 volt over a meter. Well, this distance, I was using this distance. What do you see? That's a good question. This is why. Wrong. Did I answer your question? What is exactly wrong? What part of a rule did I break? What do you think? The points must lie on the same electric field line. Electric field lines, we just said, point straight down. So electric field lines should look like this. This one or this one. So points B and C do not belong to the same line. So I could not use those points. But instead, what points should I have used? A and B. So do I have? Yeah. So correct. Equals delta V over distance. Delta V is 20 volts, distance is 20 centimeters, 0.2 meters, to 100 a volt over a meter. That's how rules work. But in order to use a rule, first one needs to know the rule, literally. If you don't know the rule, you just can't use it correctly. That's why physics requires memorizing, not thinking. If someone told you physics requires thinking, they lied. Well, now we make a generalization. Very simple. Even if electric field is not exactly uniform, if those 2 points located very close to each other, we can still treat electric field as almost uniform and use exactly the same relationships. Close means, of course, this distance should be much smaller than like size of a system, like size of electric plate or something else. This is the summary. Nothing new here, just everything in one slide. And this is another summary. Some parts of what we learned related to a process which we call mapping. I want to generate electric field here, and I want to see it. We know that we could have used grass seeds, but if we used grass seeds, we could see lines, but we couldn't say anything about actual strength. So we need a more accurate approach, and first we need a source of electric field with just a power supply, a battery, anything, a generator. And we need a device which could measure. Measure what? We actually cannot measure electric field directly, but we can measure voltage, potential difference directly. We just have to go to Home Depot and buy a multimeter. And of course we need to plug everything in and connect everything in a good way. So let's see if it never works until you flip the fingers. So you should look at this paper. This is a carbonized paper. It has a layer of carbon, and the carbon is a conductor. So if I connect these two electrodes to a power supply, here, in this region, we should have electric field generated between these two electrodes. I have to use conductive wires. Those not made of plastic. Those made of copper. So opposite electrodes or terminals should be connected to opposite electrodes. Now, what's wrong? Okay, let's say 200 volts. So between this electrode and this electrode, I am generating 200 volts potential difference. It's going to be on one of the slides in the future, but electricians and many physicists, they don't say potential difference. They use one word, voltage. That's it, because they measure volts. Now we need to switch to multimeter. So multimeters might measure alternating current of voltage. We need constant, and 200. Now it measures nothing practically. Now, depending on how we connect, we can see a negative number or a positive number, of course, because it measures potential difference between the grounded electrode. The black means grounded. Grounded means connected to the earth. It means this potential is set to 0 automatically. And this electrode measures potential relative to 0, and it could be above 0 or below 0, depending on how we connect it. So, no. Electrical potential energy is charge times electric potential. Energy includes charge in it, always. So, well, not exactly 200, there's some resistance. So this is 0, and this is 168 volts higher. And if I move closer and closer, the potential drops. Why? Well, if you remember equation, potential equals E times D. So assuming E, electric field strength, remains almost constant, if we decrease D, we decrease potential difference. If we increase D, we decrease potential difference. Now what can we do? Well, technically I can just connect this permanently. So I can measure electric potential at different locations, 58. So I can move my electrode and find another place with a 58 volts. Actually, let's do 48, wherever. 48. I can find more and more points with exactly the same potential. 48. Now we can connect those. This line has a name. How do we call it? Equipotential line. 48 volts. Now we can find another. You see, it's safe to touch it. Maybe not. 86. How does electric field point? Does it point to the left or to the right? There is a rule. From high to low, does it point like this? No, it must be perpendicular. So electric field lines should point like this. Of course, close to the edges, you will see some bending. But in the middle, they almost uniform. That's it. And we can actually calculate the electric field strength. You know, if we know potential difference and distance, that's it. So this is just an illustration of what you're going to do next week in a lab. Mapping. Any questions? Well, and last note. So again, the review. And remember, we've mentioned several times, electric field lines, equipotentials, perpendicular. Well, now we can actually see why. This equation is just taken from the yesterday. This is now the same equation written in a way you can read it. This is how we were able to calculate a work done by a force in mechanics, Py105, product of three variables. Now we know that if we move a charge along equipotential, potential doesn't change, there is no potential difference, work must be zero. So if the product is equal to zero, that only means one thing, at least one multiple must be equal to zero. If it's not the force, force equals charge times field. If it's not a displacement, that must be cosine. And cosine of which angle is equal to zero? 90. That is why equipotentials and electric field lines must be perpendicular to each other, no matter what. Now we've talked about conductors and insulators. A dielectric is another word for an insulator. And the difference is simple. It's very hard to make electrons travel inside an insulator, but it's very easy to make electrons travel inside a conductor. So let's say, I wasn't sure if I might need this. Now I know I will need it. I've got a cart prepared. Let's say we have an aluminum sphere. I can take a plastic bat, rub with the fur, touch the sphere, and we know now it should have a charge. But where? An insulator or dielectric keeps an electron where it's been placed. They can't move. But in a conductor, they can move. And they will move because of simple reason. They repel each other. So they will move until they stop. And when they stop, equilibrium is reached. And if we have a sphere, everything is the same for every electron. They would, the distribution would be uniform. Average distance between all extra electrons would be the same. What if we have something like a pair? In that situation, actually, we're going to have more electrons here than here. Well, we don't have to prove it, but we need to remember that in addition to electrons, there are other forces acting on those extra electrons. They remain because something keeps them. What? Those protons, which inside of this object, they keep electrons inside on the surface. Otherwise, they would just fly away. If we keep adding electrons, of course, it makes more and more charge. Electric field will be stronger and stronger. And there's a limit always. At a certain point, we put so many electrons that any additional electron will be repelled so strongly that we just can't keep adding anymore. There's a limit we can add a charge. That limit depends on many circumstances. But if you look at two electrons, like here and here, of course they should repel each other. But they also being attracted by protons inside. And depending on the curvature, those protons help slightly differently. So in the end, we can store more charge at the pointy places. That gives stronger electric field here. But the most important fact is this surface must have same potential everywhere. Why? Because it, well, we put electrons, we wait a fraction of a second, they run away, eventually due to internal resistance, they're not moving anymore, they stop. If they stop, that means there is no force anymore acting parallel to the surface. If we had different potential here and here, potential difference would create electric field. That electric field would create force. That force would make him move. In equilibrium, when equilibrium is reached, that means no force, no that electric field, and there is no potential difference. That means electric potential of a conductor is the same everywhere. And of course, the value of that potential should depend on the charge we put on it. No charge, no potential. More charge, more potential. This relationship depends on the shape, on the other properties. And this coefficient, which relates how much charge we can put and what potential will be generated because of that, has a name, the capacitance. This is basically an official definition of capacitance. We could rewrite it. A capacitance physically equal to amount of charge we need to add to this object to increase its potential by 1 volt. That's it. And for different objects, that amount is different. If we have a very large sphere, it can store a lot of charge. And for the very large sphere, we would need a large amount to increase the potential by 1 volt. For a small sphere, less amount. But we're not going to talk about spheres. We're going to talk about simplest situation, a parallel plate capacitor. It's not one conductor. It's two conductors close together. Why? Well, because if we place positive charges here and negative charges here, they attract each other, so that increases capacitance. That's it. And another thing good about this, we know how to calculate electric field. It's supposed to be almost uniform, and we know everything about uniform electric field. We know how to relate potential difference between the plates, distance between the plates, and electric field strength. This. And we know that electric field strength is related to the amount of charge and the area of the plate. So this is a definition of a new physical quantity called capacitance. And if we just work it around algebraically, turns out the capacitance of a parallel plate capacitor is proportional to area, which is natural, more area, more space for electrons to be stored, and inversely proportional to distance. Why? If we decrease the distance, they attract weaker and weaker each other. And this coefficient is just a number we've seen before. This is very important slang note. People say the capacitor is charged. And sometimes people think that only one plate is charged. No, it means both plates have charge. One has a positive charge, another has a negative charge, and magnitudes are the same. Now, we can increase the capacitance by adding a dielectric between the plates. When capacitor is already charged, which means I can do something like this. So then I have opposite charges. And if I don't touch it, I do not change the amount of charge. Even if I move plates closer and farther, that doesn't change the amount of charge. If I place something in between, that doesn't change the amount of charge on the plates. But this dielectric will be polarized. Remember an example with a bat and a wood? And that polarization actually decreases total electric field inside. So we can put more charges on it to get exactly the same original potential difference. That is why if we want to increase the capacitance of a parallel plate capacitor, we can fill it up with something, with wax, for example, plastic. And to relate the new capacitance and the old capacitance, this, the capacitance of a capacitor with vacuum or air doesn't do anything. And this is the capacitance with some material. We need to add one number, This is a Greek letter kappa. Its name, a dielectric constant of the material. And it depends on the name of the material. Dielectric constant of material might be 1.5, 3, 5. The wax has 3. So this completes the theory. The first part of the theory, a definition of capacitance and how to calculate the capacitance of a parallel plate capacitor. All we need to do now is just an example, and we will be done for today. Calculate the capacitance of a capacitor consisting of 2 parallel plates. The shape doesn't matter, but it's just easier to draw 2 circles. Could have been square, again, triangle. Does not matter if we know the area. So let's say this plate carries positive charge, this plate carries a negative charge. Here, between the plates, we should have a uniform electric field which points from plus to minus, from high to low. Here, between the plates, we also should have a certain potential difference, or people call it voltage. And this capacitor, turns out, is being connected to a power supply, or where's my power supply? Here. Yeah, the power supply. All I need just wires. And if the power supply supplies 100 volts, that means potential difference between the plates is equal to 100 volts. And since we know all parameters, dielectric constant of wax 3. This is 8.85 times 10 to the negative 12. Area. I just need more room. Oop, come back. So C is equal to K epsilon naught A over D, 3, 8.8, that's the times 10 to the negative 12. Area. This is the part when people might make a mistake because we need to convert centimeters squared into meters squared. 1 square centimeter is 10 to the negative 4 meters squared. Oh, okay. Divided by the distance. So it's completely filled with wax, and the wax is 1 centimeter thick. So the distance between the plates is 1 centimeter, or 0.1 of a meter. So now we need to calculate this number. If you work out the units very carefully, you will get a meter, which is weird, which is why we don't call a unit of capacitance meters, we call it farads. Please, anyone, tell me the number, 3 times 8.95, etc., etc. Negative 11 farads. 85 times 10 to the negative 12, that's, I would expect to be the answer, pica farads. people usually convert powers of 10 into corresponding prefixes. Nana means -9, pica means -12. And what can we do now? Q equals C times delta V, 85 times 10 to the negative 12 times 100. So, yeah, 85 times 10 to the negative 12. So, 85 times 10 to the negative 10. That probably would have been converted into nano. So 8.5 nanocoulombs. Any questions? All right, in that case, thank you very much. We are done. And today, please do your thing. And don't forget that on Monday, our class will take place downstairs in the different room, B23. Yes.
What is this? What's that?
That's a unit of capacitance, farads.
Farads?
Yes,
What is farads?
a unit. Oh, you know, we measure distance in meters. We measure speed in meters per second. No. Well, you can, yeah, this goes downstairs. That goes downstairs. There is one more cart with big capacitor. It goes downstairs. Because on Monday and Tuesday, the class takes place downstairs.
So farads is like a circle with a line inside.
It's a Greek letter phi. That's all I can say. Well, it's like, it is literally like it is.
So like furniture?
Circle,
Oh, okay.
it's a Greek letter, capital F,
Okay,
capital
go
phi,
to the previous slide. Yeah.
previous to,
The one that, the last slide, the last.
oh, the very last slide. Oops.
And after you get this, and what do you do?
This charge equals capacitance times voltage. Delta V is 100.
Okay.
This number is this number.
Okay. You just times 100.
Just multiplied by 100. Yes.
I have a question. I was doing the practice problems the other day, and I was doing, for number 2 in the practice problems, it was asking how many excess or absent corresponded to charge on each sphere. So I solved for this, and I got this right. And then for this part, I just divided.
What is this? That's a charge.
The resulting charge.
Probably microcoulombs. So you didn't take into account that micro means 10 to the negative 6th, I suppose.
Well, I tried that, and because the answer is 10 to the 12, and I kept getting 10 to the 18. And then I looked at.
No, this is, see, you're dividing by this.
Right.
If this number is correct, that's supposed to be 1.35 times 10 to the negative 6th.
Okay.
See, your old charges are micro. And but this is not micro, this is coulombs. So you divide in microcoulombs and coulombs, you mix in two different units.
Okay.
That's most probably the reason. Yes. Anyone?
Is there any way I can go into the lab room and check and see if I left my calculator in there?
Yeah, just give me a minute.
Okay, yeah, no
Yeah.
problem.